All right, so blending. So we're moving into asphalt. So what are the two ingredients of asphalt? Aggregate and asphalt cement or binder. Okay? So just like concrete, the aggregate is the backbone structure of asphalt. Okay? So we don't use asphalt to build tall buildings, right? At least I haven't seen one anyway, but you never know, right? So and then as I recorded the lecture, so I have the lecture recorded. The asphalt cement is the glue. The binder is the glue, kind of like the cement for concrete. So it's very important that the gradation for asphalt is actually even more critical in asphalt than it is in concrete, okay? Because that asphalt, it's just aggregate, air, asphalt. That's it. Glued together. And it gets heated up, okay? So what we need to do, we need a very specific, well-graded mix. Remember those terms, poorly graded, well-graded. Poorly graded is one size, well-graded was several sizes. And then there's like gap graded where they miss sizes, okay? So what we do in aggregate blending is that we need to grab some of this pile, some of this pile, some of this pile, and mix it together, and we gotta meet a spec to have a really nice, well-graded mix. Because remember, what do we want? We want friction, particle on particle contact, right? And we don't want flat and elongated particles. And we're doing that test, okay? That's very critical in asphalt, because remember that asphalt layer on that road is only this thick, so those wheels are beating on that, right? So those can break, okay? We need fractured faces. We actually want 2 fractured faces to create that friction, okay? And then all the same aggregate properties like toughness, freeze-thaw resistance, LA abrasion, P200, those are also important in asphalt, okay? So, in the real world, I can't remember which homework set we were in, number ASTM C33, there's all those different stone sizes, 67, number 4, etc., right? Those are the common stones that are made. And then in asphalt, they'll vary from that a little bit, and it'll be common, okay? So, when we do, just like concrete, we have coarse aggregate and fine aggregate, right? We also have coarse aggregate and fine aggregate in asphalt. Number coarse aggregate is retained under number 4. Fine aggregate passes number 4, retained under number 200. Okay, so we cannot make one stockpile that meets our gradation specs. It's almost impossible to make a good asphalt mixture. HMA, hot mix asphalt. Okay, do not call it blacktop. Got it? Okay? So, what we do is we blend stockpiles together to create a nice mixing to meet specification. So when you look here, I'm in example 1, if everybody looks here, you got bin 1 and bin 2. Okay? So if you look there, bins, you can pretend bin is like a stockpile. So when you go to an asphalt plant, when you look, you see these. Just like at Green and Gold, they have the different bins, for the different, it's the same thing in asphalt. Bin 1, bin 2, bin 3, bin 4, bin 5. Those are all different, where they fill them up, right, with different stockpiles, okay? So, and then what they do is they open them up, they get a percentage of this, a percentage of this, and it gets all mixed up in the asphalt world, okay? So, does this look familiar? Sieve size? So gradation is a very important tool in cement and ags because we use it for concrete mix design and we also use it for hot mix asphalt design, okay? So bin, you can consider this a stockpile, bin 2, okay? And these are percent passing, okay? Remember that column way on the end there? Percent passing, okay? JMF. Job mix formula, okay? Aggregate blend used for mix design, okay? So if this is 100%, anything above that is also 100%, would you agree? Right, so I'm just gonna fill this in. All right, now let's look up here. Does everybody see this okay? I can zoom in a little. Maybe what I'll do is I'll lock it so it doesn't, there we go. All right. Percent blend, okay? This percentage plus this percentage has to equal 100%. This is the magic key, right there. So if I have 2 bins, 3 bins, 4 bins, 5 bins, 6 bins, bin 1 plus bin 2 plus bin 3 plus bin 4 plus bin 5 has to equal 100%. Otherwise the math doesn't work out, okay? So with that, let's talk about economics for a second. Say bin 1 is $100 a ton to have it delivered to the asphalt plant. Bin 2 is $10 a ton to have it delivered to the plant. And the asphalt production contractor is getting paid $50 a ton no matter what. Which one do you think they want to use more of? Probably bin 2, right? The cheaper one? Economics. Okay? So that's one consideration. However, we can't do that because we need to meet specifications. So we're going to have to use bin 1. So blending is actually a trial and error design. That's why Excel spreadsheet, does this kind of look familiar? And some of your, yeah, okay, yeah, awesome, right? So this is why Excel comes into play. So we can vary it, okay? So I'm going to show you how we create. What we're doing is we're actually going to create the JMF, the job mix formula, the blended percent passing, combining these two stockpiles together, okay? So somebody give me, what's the percentage of bin 1? Just somebody shoot out a number. Between 30, 20, 35?
34.
34. 34%. Okay? So what does this bin have to be? 100 minus 34?
66.
66%. Okay? All right. So with that, okay. Is that the decimal form? Do you agree? Okay, now my JMF. So for this one, I'm going to take 100.0 times 0.34 plus 100.0 times 0.66. This line is 67.6, right? I'm leaving this one alone, so one of them has to be turned into a decimal. So it's easier just to turn these two into decimals, right? Would you agree? Than trying to turn all these into decimals. 67.6% passing. Bin 1, I'm going to use 34% of that bin plus 100% passing the half-inch sieve on bin 2, and I'm going to use 66% of that bin. That's how you do a JMF. So it doesn't matter how many bins, I just keep doing it. It's this times this plus this times this, and you just keep going, okay? So can somebody give me the 3/4 inch value? Wouldn't that be 100 still?
Yeah.
100 times 100, right? Okay, 100.0. All right, so I'm going to call names. So, Gabe, what is the half-inch sieve?
$15.16.9.
That's not correct. Try that again. 67.6 times 0.34 plus 100.0 times 0.66. Michaela, can you do the 3/8 inch sieve? Brooke, you do the number 4 sieve. Matt, you do the number 8 sieve. Alec, you do the 16 sieve. Cameron, you do the 30 sieve. Blake, you do the 50 sieve. Josh, you do the 100 sieve. Angel, you do the 200 sieve. So what do you get for the 1/2 inch sieve there, Gabe?
88.9, so 88.
So
89.0.
89.0, okay? So I want everybody to calculate each one of these so we can check each other, make sure we're getting the right answers. 89.0. 3/8 inch sieve,
69.2.
69.2. Number 4 sieve,
47.7.
47.7. Number 8 sieve, 8 sieve.
I'm trying.
Okay. Take your time.
.9.
Okay. Number 16 sieve,
29.8.
number 30 sieve,
20.9.
number 50 sieve,
10.4.
number 100 sieve,
2.9.
number 200 sieve,
I said 2.9.
100 sieve. You said 2.9. What's number 200 sieve? Sorry. Angel, you're doing the number 200 sieve.
Yeah.
1.5
Yeah, I did 1.5 times 0.34
plus
And then
5.6 times 0.66.
right?
Yep. What do you get? So 100. Josh, you got 2.9, right, for 100? Everybody's calculating all these to make sure we're all on the same page, right? And practice for your using your calculator.
I got 4.206.
4.2? Okay, that seems about right. So everybody agree with those numbers? Just do a couple random checks on other people. Just so you understand how to, the key is using your calculator. So you took 1.5 times 0.34 plus 5.6 times 0.66, right, Angel? You shouldn't have to do any parentheses or anything. It knows the order of operation, and then you hit enter and you get, so we round that to the nearest 10, 4.2.
I think the number 100
Number 100,
is, I got 5.6.
okay.
I don't know, me too.
Josh? Want to double check that?
Yeah, I typed it in right.
That could be an issue, right?
Oh, I know what they did.
Don't worry, your road just failed. No big deal.
Yeah, that's right. Yeah, it's 5.6.
5.6? All right, nah, that's no big deal. I'm not making fun of anybody. It's just, you always check your numbers, right? All right, everybody make sense how to do this? Pretty, okay? All right. So that was easy. The days are done. No, I'm just kidding. Yeah. Now, let's go to example number 2. Now, before we could just pick random percentages of each bin, right? But now, we need to get a specification. We gotta meet specification, okay? And I'm gonna show you that specification and we'll go over this again, so I'm gonna go to here, I'm gonna go to 460. Let's see here, payments, 460. Alright, so here's the DOT. Here's their sieve sizes, here's their mix sizes, and here's their specification, basically, okay? So for the 1 inch, it has to be 100% passing. 19 millimeters is 3/8 inch, it has to be from 90 to 100. 12.5, that's a half inch sieve. 90 max, so that's 0 to 90. Then 2.36, I think that is the number 8 sieve, has to be between 23 and 49%. And then the number 200 sieve, which is 0.075 millimeter, it is 2.0 to 8.0% between that, right? So you notice something different? This is a whole number here, right? And then this is a to the 10th. Okay, we'll talk about that. So that's kind of where these numbers come from, okay? It's a spec. So now we need to figure out our blends to meet this spec. So the trick to this, because it's trial and error, what's our range between 90 and 100? Is that 10%? What's our range between 95 and 65? Is that 30? 80 and 35, what is that? 50, 45? This is 40. This is, oh boy, 33. And there we go. This is 20. And this is 5. Okay? All right. So, the best way to do these blended percentages is I try to meet my spec of my tightest tolerance, specification tolerance. What does that mean? So my number 200 sieve only has a 5% tolerance difference, right? Then my next toughest one is what? My half-inch sieve, that's only a 10% tolerance difference. So typically that's where you want to start, because literally you could be doing this all day long if you're looking at trying to meet number 4, right? Because most likely you're not going to meet this. So if I can meet the number 200 spec and the number half-inch spec, majority of the time the rest of the specs will fall into place. Okay? So now, does that kind of make sense? Find your tightest spec. So we're gonna concentrate on the number 200 sieve. All right. So if I just use 100% of bin 1, am I gonna make it? No, because that's 1.5%, right? So that means I gotta add some of bin 2, right? Okay, if I use all of bin 2, will I make it? Yeah, right? Isn't 5.6 between 3 and 8%? Right? But you know I'm probably not gonna meet somewhere else, okay? So I have very little passing here and some passing here. So now the question is, so I can't make this 100%. So would I do 90-10? 80-20? See that this is where you got, so I need some of this to bump it up to 3, right? So what do we think? What do you think for bin 1? Between 90 and 70, which one do we want to go for? See, this is why it's called trial and error. What do we want? Should we try 70? 75? 75? Matt likes 75. All right? 75%? So that means this one has to be 25%, right? Do you agree? Because of the number, we have to meet 100%. Okay. So this is 0.75, this is 0.25. All right. So now, Gabe, can you calculate the number 200 GMF, job mix formula? So you take 1.5 times 0.75 plus 5.6 times 0.25. And Michaela, can you do the half-inch sieve, please?
2.5.
Oh. Never mind, Michaela. Everybody get 2.5? Yeah, I hear yes. Are we in spec? Are we in spec? Is 3, does it say 3.0 or 3? It is in spec, right? Because when I'm gonna report my results, you'll report your results to what the spec reports the results to. So this one is a whole number, but on DOT it's to the 10th, right? So we're really close, aren't we? So, all right, now Michaela, so we're really close, so we're gonna round that up to 3, right? So Michaela, can you do the half-inch sieve and see what we get? Oh boy. 75.7. We didn't meet that one, did we? We need to be at least 90 or 89.5, right? Right, Alec? So guess what? We gotta start over. So, okay. So what do we, so we need more of this, right? And we need more of this, because this is only 67.6. We need to get it closer to 90, right? So do we want to add more of bin 2, right? To get more percent passing, right? To make it finer. So we want to add more of bin 2. So we want to bump up this number. So which number? What do we want it to go now to? So we know 75 and 25 doesn't work. So what should we do with bin 2?
35?
35, okay. And then this will be 65. So this is 0.65, this is 0.35. All right, Alec, can you give me the number 200 sieve now? And Matt, can you give me the number, the half-inch sieve, please?
$2.9.
Okay. Matt, half-inch?
78.9.
Jeez. All right. Still didn't make it. We're getting closer though. Let's see how this is a pain in the butt. So now what do we want to do?
50/50.
50-50? Okay, let's try it. So you can see why spreadsheets work great, don't they? All right, Josh, since you said 50-50, you calculate the number 200. Angel, you calculate the number half-inch sieve, please.
I got 83.8, so 84.
For what?
Half inch.
The half-inch, 83?
Yeah.
All right, we didn't even pass that. What do you get, Josh?
3.55.
Okay,
So 3 point.
right, so,
6.
well, guess what? We're still not even close to between 90 and 100, right? So guess what? We're using more bin 2 than we're using bin 1 now, aren't we?
You go 30/70.
Let's go 30-70. Okay. See how this is working? When it comes with experience, you kind of know. So we're gonna go 30-70. Is that what you said, Angel?
Yeah.
All right, now, Blake, can you give me the number 200 sieve, please? Cameron, can you give me the half-inch sieve, please, now with the 30-70%? Please. You guys are gonna be famous. You can get autographs from the other group. 4.4. Okay. Don't worry, this is only gonna be on Blackboard. I'm not gonna, well, I'll put it on the YouTube, but
90.3.
90.3. Oh, look at that. Okay. Hey, I'm guessing this is still 100, right? All right. We made, this passes, so this will be 4% if we round it to the whole number, and this rounds to 90, right? So, okay. Brooke, can you do the 3/8 inch sieve? Gabe, the number 4 sieve. Angel, the number 8 sieve. Josh, the number 16 sieve. Alec, the 30 sieve. Blake, the 50 sieve. Cameron, the 100 sieve. Michaela, the 200 sieve.
Want me to do it again?
No, I just, did I give everybody one? Somebody has one. You didn't get one? All right. All right. You can do a 100 sieve. You can check numbers.
Okay.
So if you don't have a number, you can check everybody else's math. And give you a little time. All right. So what do we get for the 3/8 inch sieve?
72.3.
Okay. The number 4 sieve?
50.5.
Okay. The number 8 sieve?
39.6.
Say it one more time.
39.6.
0.6. Okay. 16 sieve?
31.5.
30 sieve?
22.
0.0?
No.
What is that? Number 50?
10.9.
Number 100?
5.8.
Okay. All right. So as you notice here, these don't have specs here, do they? So this is going to be 90. This is going to be 72. This is going to be 51. This is going to be 40, because I'm looking at the spec. This is going to be 32, 22, 11, 6, and 4. Do we meet specs in all of them? These, so this one goes to that. So 90, 72, yes. 51, that's between that. 40, yes. 22, yes. 5 and yes. No spec for the 100, yes. Oh, wow, hey? Good Lord. Does that make sense? This is what blending is, okay? So remember, bin 1 is more, well, that's good, because bin 2 is cheaper, right? So we can even, so just go to the, typically you can go to the whole number, but we can actually go to the nearest tenth, we can really get it close if we want to, okay? Any questions on that? We're good? All right. Now, let's talk about some definitions. These are super paved definitions from ASTM. They're different than concrete definitions, okay? So you gotta switch gears with your brain. Nominal maximum size. One sieve larger than the first sieve to retain more than 10%. Retain more than 10%. So if it's retained more than 10%, so now you're looking at your JMF. So what is that passing? Would you just take 100 minus 10? 90%, right? Okay, so from this data here, what's determining our nominal maximum size? It's the first sieve that retains more than 10%. More than. So does the half-inch sieve retain more than? No. That's right, that's retaining 10%. Would you agree? So be careful of that. So our first sieve that retains more than 10% is the 3/8 inch sieve, right? Because we're at 72. Would you agree? 100 minus 72 is 28. So it's retaining 28. So that's the first sieve that retains more than 10% is the 3/8 inch sieve. However, one sieve larger than the first sieve. So our nominal maximum size is the 1/2 inch sieve, right? So this is our nominal maximum size. It's the one sieve larger than the first sieve that retains more than 10%. So everybody see that? Read that out. One sieve larger than the first sieve to retain more than 10%. It doesn't say more than or equal to, it says more than. That is our nominal maximum aggregate maximum size. So 1/2 inch. Now let's determine our maximum size. One sieve size larger than the nominal maximum size. Alright? Well, this is our nominal maximum aggregate size is 1/2 inch, so that means our 3/4 is our maximum. Make sense? How I read that out loud? So could you also say that the maximum size is 2 sieve size larger than the first sieve that retains more than 10%? Yes, right? Because this is one sieve larger plus another sieve, so 2 sieves, okay? All right. Any questions on those definitions? That make sense? This is asphalt world. This is weird, I know. We're switching gears. We do things differently. Okay, now, how to plot the maximum density line. And we'll be doing this. Draw a straight line from the origin to 100% passing of the maximum size. Okay, so we'll go back to this, all right? So basically, you know your gradation, 0, 0, up to the 3/4 inch at 100% passing. Okay, so we'll come back to this. All right. Now, I'm going to hit pause for a second. All right. Now we're going to plot. We are going to plot all our data points. Okay, so some reason in the asphalt world, they have this lovely looking 0.45 power gradation chart. So if you look here on the left side, that looks familiar, doesn't it? Percent passing, right? 0 to 100. On the bottom here, sieve opening raised to the 0.45 power. Oh boy, what in the world does that mean? So literally they take the sieve size, so 1/2 inch is 12.5, and they raise it to the 0.45. That's that little caret key, like you're squaring it. Okay, that's what that means. So it's 3.11. So the 1/2 inch sieve, right here, see this? On top here, that they actually label the sieve sizes so we don't have to do any conversion. Yay! Right? Is 3.11. So if I look right here, see, here's 3, 3.1, 3.2, 3, 4, 5, 6, 7, 8, 9, 4, right? Okay? Now I want you to notice something. So so all the sieve sizes are raised to the 0.45. I don't know why. I haven't read, I don't understand the research on that yet, so I haven't had time to read it. It's great reading material. Okay? All right. Now I want you to know something. So far I've taught you that the grain size gets smaller as I go to the right. Now you notice this is backwards. The sieve size is going to the left. So the asphalt world likes to go to the left. In soil mechanics in my textbook that you use next year, the same gradation, they go to the left. So it doesn't matter as long as that's why you just label it, okay? So with that, so now I'm going to teach you how to graph these things by hand, because you already know how to do this, but we're going to graph this. All right. So same as concrete, we need our first data point has to be the first sieve size that is 100% passing, which is 3/4, right? So I'm plotting the JMF. I'm plotting the JMF versus sieve size. Okay? So our 3/4 is 100%. Okay, so I'm going to put my little dot here. Remember, I'm going to put a dot here, then when I'm done, I'm going to put a nice little circle around it, right? And use a flexible curve, so if you don't have it, no big deal. Okay. 1/2 inch is 90%. So I'm just going to go right down the list here. here's my 1/2 inch, 90%. 3/8 is 72, right? 72, here's 70. 72 is right about there. Number 4 is 51. Okay, I'll move that up so you can see it. Number 8 is 40. So here's my number 8 sieve. I go down to 40. All right, number 16 is 32. Number 30 is 22. There's 30. Go down to 22. Number 50 is 11. Okay. Number 100 is 6. So here's 50. This is the 100 line. So that's 6. So that's right about there. And then number 200 is 4. So it's a little bit below half. All right, so now what I'm going to do is use a circle template and just use the consistent size, and I'm going to put a circle around them all. If you have one, great. If not, you get to do this twice because you have problem 3A and problem 3B. I want that circle to be big enough so mine are a little bit small, but I started with it, so I'm going with it. Okay, so that's what we start now. So now, flexible curve, remember this guy? Okay. Remember, we connect 3, it's a smooth transition. So you just put this sucker on here. I do not draw through my circles. I connect my dots. Okay. Gotta get this bent. Get them. Okay. So you can see I have my line. Here's my dot, dot, dot. I have this connected. I start here, do not go completely through the circle. I stop at the edge of my circle. So now I connect these two, I match this two, and then what I want to do is connect that third. Okay? Because remember, you want to keep it as a smooth transition. Alright, so now I'm going to connect these two. So I got to just move my flexible curve down. So I'm going to match this line. So basically, so you can kind of see what I'm doing here. Alright. I matched that one best I could. And now I'm going to bend this sucker down. There we go. Just want to make sure. And I keep bending it best I can. Sometimes what you do is you connect the last three, and then there we go. You kind of bend her down. flip over to here. Okay, so you can kind of see how I'm matching here. And then this one is almost near impossible, so you gotta pretend. There we go. Whew. See how the nice smooth, it's not the best, so I try to get this line, okay, see, I didn't go all the way through the circle, so just match it the best you can. See how it's all nice, it's smooth, there's no sharp corners or bends or anything like that? Okay, so that's graphing, so remember that part? Okay, now let's plot our maximum density line. Again, what was our maximum density line? Draw a straight line from the origin to the 100% passing of the maximum size. We determined our maximum size was 3/4 inch, right? From all those definitions. So now you're gonna use a straight edge. Anybody have a long ruler I can borrow? Long. I can use a piece of paper too. That'll work. Actually, can't reach her. So I'm gonna go from 0 to 3/4. Oh, this barely makes it. Thank you, Peter. 0 to 100% passing my maximum size. It's a straight line. Okay? Maximum density line. So I'm going to do a quick definition for you. What that is, in theory, because we put all our sieve sizes to the 0.45, is if our data points fall on that maximum density, in theory, that's as tight, as packed as that mix can be. Least amount of air voids, in theory. Okay? Make sense? That's in theory. So if all our data points are in there, we don't have hardly any air voids in space between the aggregates. Okay? But in asphalt, we do not want that. Because remember, just like concrete, we want the cement paste to completely coat the aggregate. We also want the asphalt cement or binder to completely coat the aggregate. So if our gradation is too tight, they call it too tight, we cannot accomplish that, can we? So we need to have a little bit of air voids in there. One, that accomplishes the getting complete coatation, get the aggregates to be completely coated by binder, and create enough space so we get aggregate on aggregate contact to get that structure. Because if we have too much asphalt binder in there, it's just going to be a smooshy mix. Okay? So this is why gradation is so important in asphalt world. So that's what that maximum density line represents. It just tells us where we are. Okay? And I bring this up in the lecture I recorded yesterday. So that's our maximum density line. Now, what we're going to do is we're going to plot our control points or specification. So what I'm going to do is use a different shape, a square, a triangle, if you have some other shape. So we know our 3/4 inch is 100%, so I'm going to put a square around this guy, nice and neat. Okay? Our 1/2 inch is 90 to 100. So I'm just going to kind of color them in this, okay? Our 3/8 inch is from 65 to 95. Our number 4 is 35 to 80. Sorry, you can't see what I'm doing here. 35 to 80. Okay, our number 8 is 20 to 60. Okay, 16 does not have a spec. 30 is 7 to 40. So 7 is, let's say right about there. All the way up to here. So 7 to 40. Get this so you can actually see. Alright. I did the 30, right? So 50 is 5 to 25. To 25. 100, there's no spec, because I'm looking at my paper right here. And 200 is 3 to 8. Here's my 200. So 3, just pretty much right on top of that, to 8, which is right on top of that. Okay? So, I'm going to make a little legend. Got my little circle here. Because we want to know what the data points mean. That's JMF. And our squares are specification, or you can call them control points. Whatever you want to call them. Specification. Okay? Alright. Okay. And then, so what I want you to do when you do this, you're going to put problem 3A or problem 3B so I know which one is which, okay, on title. Okay? All right, now if I look at this, okay, so one, they call these control charts, okay? So as McKeefrey and Sons is producing Northeast Asphalt, with Aggregate, they're going to be running a gradation, and they're actually going to have a spreadsheet on each sieve. They're going to graph these, right? And it's a working spreadsheet. So as the tests go on, so if their data points get close to their control points, Northeast Asphalt is going to talk to McKeefrey and say, hey, the number 8 sieve, we're getting close to a specification limit. So you got to do something. McKeefrey, you better do something. Okay. Now let's look at the half-inch sieve. We're right on it, right? So it could fall below, right? So typically, what the DOT does, it's called the percent within limits. Okay. So as we in aggregate world, we can't instantaneously make a change. I mean, like, okay, I call Northeast Asphalt calls McKeefrey, hey, my number 8 sieve is off. Okay, I'll change that, right? And the next load is fixed. No. So they have time, you know, the next couple sample interval, however many tons that is, they should see a correction. If they don't correct it, then they get a, based on the percentage within limits, percentage of that control point, they'll get a deduction in pay. Okay, they'll get warnings basically. So basically, you want to see, you'll see these data points as wander between these 2 points. So it's a graphical, visual thing to say, hey, what's going on here? And another thing is, if these data points, see how close these data points are to this maximum density line? That could be an issue for us too. So there will be a graph with the maximum density line, and we can watch the data points that go. 1A, we're within the specification limits, the control points. B, is it starting to move towards that maximum density line? Because if it starts doing that, our asphalt mix is not going to be the best. So it's 2 ways to kind of check it. Okay, kind of a nutshell, you know. So this is kind of what it looks like. So there's a lot of information that you're looking at there. There's this gradation and this maximum density line, and it tells you a lot of information right there without even looking at numbers, does it? You can tell, hey, I'm good, right? My data point is in between my boxes. Okay? Any questions on how to graph that? Make sense? Ready to go over your homework? Yeah. All right. So this is in lecture materials, learning plan 6. So here's the video I just made yesterday. Okay. Here's the blending examples that we just did. Here's the specifications which I just opened up. So here's homework set 8. Here's homework set 9. All right. Okay, it says, please attach your working spreadsheet as a separate file on the Blackboard. Please attach your printout of your worksheet and hand graphs in the Blackboard as PDFs. I'll explain that. Okay? Homework set 9. All right. Says 1, develop a Microsoft Excel worksheet that will calculate the resulting blend, JMF, when varying percentages of different aggregates are selected. The worksheet should allow for up to 5 bins and calculate all Wisdot required civs as well as the 16, 30, 50, and 100 as listed below. Okay? So here's problem 3A. 3A has 3 bins, but your spreadsheet is going to have 5 bins. You're going to copy this data into your spreadsheet. Here's 3B. 3B has 4 bins. You're going to copy this data in your spreadsheet. Okay? Let's go look at a spreadsheet. Come on. All right. This is, see how I'm naming that file? This is when I see that, when it's in Blackboard, right? Because I open it up and I need to know who's I'm looking at. HMA blending, Tomlanovich. All right. Here we go. All right. Okay. So, this has to be functioning, obviously, right? Take pride in your work, okay? So here's all those sieve sizes, right? That matches the homework problem. Let me go. See, here's all the sieve sizes. Down here, all the way down here, right? Okay? So that's on this side of the spreadsheet, right? Okay. Bin 1, bin 2, bin 3, bin 4, bin 5. Okay? All right. JMF, job makes formula, right? So I'm going to delete this. I'm going to turn my body here so I can. Okay. So we know that has to equal 100%, right? So let me hit the delete button. So how do I do that? Equals. Remember doing this in Excel and Intro to Civil, right? Equals this plus this plus this plus this plus, I hate that when it does that, you have to shrink it, so H5. Check. Okay? Remember, this has to equal 100%, so if I change this to 78, look, it's 101. Okay, because number what am I doing? I change number of percentages to meet the specs. Okay? Make sense? Pretty easy? So this has to be 77. Now, I want you to notice something here. Here's a trick. See this? See these cells? See it? Look at, when I type here, this says number up here, right? Now, if I put it right here, what does that say? Percentage. When you identify that cell as a percentage, when you multiply it out, it automatically knows is to move the decimal spot back 2 times. So you don't have to sit there and divide one of them by 100, right? Ding, 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 ding. Like that? Okay? So that's that. So remember, that has to equal 100. Okay? All right, so these are all the gradations, right, from the problems that are in here. So you notice you can put any number in here because as soon as I put a 0 here, any number times 0 is what? 0, so it's adding 0. So it doesn't matter what number I have in there, does it? And right here. Because if this says 0, it's not going to add it. Okay? So don't worry about that. So let me delete this. Now, Does everybody know remember what an absolute cell is? And a relative cell? I'll reteach you. Okay, so the formula is, could I do this also a different way? I'm just gonna back up a step. Could I put sum? Right? Select those cells in parentheses, same thing. Right? Remember, this is just a big old fancy calculator. All right, okay. So, we gotta take this times this, plus this, times this, plus this, times this, plus this, times this, plus this, times this. But, we wanna keep that cell, right? Does this cell change? So if I take this one times this, we always wanna multiply all of these by this one, correct? So we wanna make this an absolute cell, and I'll show you how to do that. So I hit the equal sign. This times this cell. Remember the old-fashioned F4 key? So watch what happens to the D5 cell. It goes dollar signs around it. It locks it. Plus this times bin 2, F4, plus this times F4. Oops, I gotta hit that first before I hit F4, right? Jumping the gun. Plus this times that F4 plus, now what's bin 5? H8, right? H8 times bin 5 is H5 F4. I hit the check mark. Okay, so if you're ever wondering what it's grabbing, you go here and you go like this. See, you can check your colors. This times this plus this times this, that, right? Makes sense? Now, watch this. See this? See that? See how that little cursor changes? If I drag that down, whoa. Now, we'll look at this. Because I did not lock this cell, I left this as a relative cell, it knows when I drag it down, it's gonna grab this one, this one, this one, and then so forth. But see, it's multiplying by the same numbers. Pretty cool, huh? Excel is a wonderful thing. Okay? So then, now what you do, you're gonna write okay, once you get your spreadsheet working, are you gonna check it with your calculator to make sure it's working properly? I would. A good engineer would do that, right? Okay? Once you get your spreadsheet working, I recommend that you sit there and you hit right click, move, create a copy, hit OK. I'm going to rename this thing. I'm going to call it 3A. Boom. Right? I know this is my working spreadsheet. I verified it. So if I screw up something, I can always go recopy it, right? Yes. Wouldn't you hit suck if you had to do that over? All right, so 3A. So now here's my specs. So now what I can do is I can start playing with these percentages. So see here I have to the 10th. If you want to go to the whole number, whatever, you know. I can keep playing with these numbers until my JMF, which is this guy, if you want. So you're always making sure you're looking at the right column. There, right? Is this between this? Is this between this? Is this between this? Is this, right? Okay? Now, okay, so any questions on how to set up a spreadsheet? So once, yeah,
So
Angel.
we're just messing with the top numbers, nothing.
Yeah. Once you get this set up, you gotta enter the data in here, right, from the problem. You're gonna enter in the spec, because once I'll talk about the spec, and then only thing you're messing with now are these numbers, right? Because you're gonna only have 3 bins for this one, right? So your first problem, this is gonna be 0. So now you're going to be messing with these 3 numbers. Okay? Pretty neat, huh? So once I get that working, so I have problem 3A and 3B, you're gonna attach this worksheet Excel format into Blackboard as one file, because I want to check your formulas, okay? Clear on that? All right, let's go back to the homework problem. Okay, when completed, HMA blending your last name and attach it. All right, review 460, okay? All right, 460 is right here, that's where I'm in, I'm gonna be looking at this table. Okay, so, problem 3A, combine the following three aggregates to produce the finest gradation. So we want the most amount passing, right? Would you agree? Does that make sense? Finest gradation, I want the most amount I can get past. Finest gradation that will meet WISDOT super paved 12.5 millimeter gradation without exceeding the specification. All right, let's go to that. So problem 3A, so you have these three bins, right? So my specification, what is it? What did it say? 12.5 millimeter. Right here, that's the number 4. Everybody see this right here? And look, whoa, right there. So my specification limits are right here. 19 millimeter, 3/8 is 100, half inch is 90 to 100, 3/8 or 9.5. Wait, that's 3/8. 9.5 is 3/8. This is 3/4. 3/4 is 100, half inch is 90 to 100. 3/8 is 0 to 90. Does that make sense? 90 max, 0 to 90. Number 8 is 28 to 58. Number 200. Now, what does this say right here? 10th? 1 decimal place. So, do I want this to all of these? Right? Look at that. Whoa. Bingo. Right? But remember, you want to look at this 10th, because if it says 90, does 89.5 equal 90? Right? So you want to be able to look at that. Okay? But this one is always reported to the 10th. So going back there, so this information here on these sieves goes right here, specification, right? Because that's what I'm comparing to. Does that make sense? Okay. Now, it says finest. So that means I want to be closer to 100 here, closer to 90 there, closest to 58, and closest to 10 here. Would you agree? To make it the finest? Now remember, which one are you going to try to meet first? The tightest tolerance, right? So mostly it's the number 200 sieve. So if I can get the number 200 sieve as close to 10% as I can, but this is going to frustrate the living bejesus out of you, because then you're going to do that and all of a sudden one of the other ones up above won't meet spec. Does that make sense? So you're just playing with those percentages. So that's problem 3A. Does that make sense? What I'm asking for? Okay. Now, when I have that, when I think I have it, when I think I've solved problem 3A, I'm going to go into my spreadsheet. I'm going to do this, page layout, set print area, and you're going to file, print, and turn it into a PDF. Does everybody know how to do that? Yeah, pretty cool, right? And then what you're going to do, you're then going to plot your solution, your JMF, versus your specification on this. Okay? And then you're going to take this and turn this into a PDF and make that and attach it to that PDF, or if you want to print that out in PDF at once, right? Okay, so you can have problem 3A PDF and problem 3D PDF if you want, or you can just do all 4 at once. I don't care. So spreadsheet, PDF. Okay? All right, so problem 3B is, now I'm going to copy my tab over. Now I'm going to put, there's 4 bins in there, right? So I'm going to copy all this data in there. My sieves are the same. And then I want to make it the coarsest for the 19 millimeter. Coarsest. So 19 millimeter, that's the number 3, that's right here. So here's all my specs. Okay. Now, if I want the courses, do I want more passing or less passing? I want more retained, right? So I want less passing. So I want to stay on what side of my spec? The left side, right? Close to 90, closest to 0 as I can get, closest to 23 I can get, and closest is to 2.0 I can get. So that's problem 3B. Okay. So once I have that done, right, I'll have 3B. I do the same thing. I make sure it meets spec. I print that out. I plot it. Problem 3B, number I'm going to put a label here, 3A, 3B. Get it all in PDF. I'm going to send it in the Blackboard. Okay. So, does that make sense, what I'm asking? All right. When does this thing due? Look at that. So are you going to wait till December 1st? So I'm going to say this on video. My biggest pet peeve is when somebody comes to me on December 1st and tells me I forget how to do this assignment. Well, now you have no excuse because you have a video to watch, right? So it's due by December 2nd at 11:59 p.m. Doesn't mean do it on December 2nd. Right? Okay? So that is the assignment. It should be fairly easy. The spreadsheet shouldn't take, you already had exposure to that spreadsheet, right? Because that's why I introduced it to you in Intro to Civil. You've seen it. So it shouldn't be any, new thing like, oh my God, I never used Excel before. No, you've seen it, you've been exposed to it, right? Okay? Any other questions? Angel?
So the graphing, you want it like physically or?
Yes,
Okay,
by hand, please.
okay.
Yep.